Hello everyone, welcome to this lecture on the Ampere's law. In the previous lecture we had got introduced to the PSED law. In this lecture we will derive what is called as the Ampere's law, and this particular law is it has a relationship with the PSED law which is similar to the relationship that the Gauss law has with the Coulomb's law. So starting point would be to determine the divergence of the magnetic field, because essentially suppose I'm introduced to any vector field. I am interested in knowing two things about that vector field. First thing, I would like to know what is its divergence, and second thing that I would like to know is what is its curl. So first let's have a look at the divergence of the magnetic field. So for this purpose we'll consider a scenario like this. So let us say I have some volume tau prime, some volume tau prime, and this tau prime is bounded by some surface S prime, and this tau prime, it contains some current density J. So we are assuming that this current density J, it is confined within this volume tau prime, and S prime is the boundary. So now, because there is this current, so a scenario of this sort could be maybe we could have some volume charge density, and inside this volume charge density, let's say that the charges are just moving around. So that is going to constitute some kind of a current density within that volume. Okay, so we have some current density J which is confined within this volume. So now we would like to find out, because this current density, we have a current density here, so it's going to produce some magnetic field at some point P. So we would like to find out what is the total magnetic field at point P due to this entire distribution. So we can use the Biot-Savart's law. Okay, so using the Biot-Savart's law, we can find out the magnetic field at this point P due to some volume element. So let's say there is some volume element d tau prime, and through this volume element d tau prime, let's say there is some volume current density which is J, and we can find out what is the magnetic field at point P due to this volume element. And this magnetic field is given by, again, the Biot-Savart's law, which is mu naught by 4 pi J d tau cross r minus r prime, which is the separation vector, divided by the cube of the separation distance. Now in the Biot-Savart's law, original Biot-Savart's law, there was a IDL, but this IDL has got replaced with J d tau, because as you can recall, IDL is equivalent to J d tau. Okay, so this is basically the magnetic field, this infinitesimal magnetic field which is produced by this infinitesimal volume which is d tau prime. Let's call this equation number 1. Then the total magnetic field at this point P, as you can guess, is simply going to be the integration of of equation number 1. So we are going to integrate this equation number 1. So left hand side we will get the total magnetic field, which is going to depend on r alone, because we are integrating with respect to r prime. Okay, so there are two variables, r and r prime. The integration is done with respect to r prime, so whatever is left behind will depend only on r, and so B is going to be a function of r, which makes sense because r is the field point. So mu naught by 4 pi being a constant, we can take it outside, and then we have a volume integral of J cross r minus r prime divided by modulus r minus r prime cube. So this is going to be the total magnetic field at point P due to the entire distribution. So now what we do is that relationship which we had used earlier also, there is vector r divided by modulus r cube, which is equal to unit vector r cap divided by modulus r square, that is equal to minus gradient of 1 by modulus r. Okay, so we use that same relation. So this quantity can be written as gradient of minus 1 divided by r modulus r minus r prime. So we substitute this over here. So now this minus sign, we take it outside. So finally what is left behind is minus mu naught by 4 pi the volume integral of J, which is a function of r prime, because J depends only on the position within the distribution, crossed with the gradient of 1 by modulus r minus r prime. So this is the magnetic field at any point P. So now I can always take this nabla outside, and there is a cross product here. Cross product means the order has to be maintained. We have to maintain the order. So I can take this nabla outside, because this nabla is the differentiation with respect to r, not with respect to r prime. Okay, when I'm saying nabla, it is differentiation with respect to r. So we can always take it outside. So when I take it outside, then an additional minus sign is going to come because there is a cross product here. So that minus sign and this minus sign will together give us a plus sign. So that gives us this overall quantity. So we'll have a curl. So this nabla coming outside crossed with whatever is left, that is mu naught by 4 pi j by r modulus r minus r prime, this integral. Okay, so this b is written as curl of this entire quantity. So this is equation number 2. So now what equation number 2 tells us is that the magnetic field B can be written as the curl of some vector field, right? Because as you can see here, this is a vector field. This is J, which depends on r prime. In the denominator, we have r minus r prime, and you're integrating over r prime. So this is a quantity which is going to depend on r. So because it's a vector quantity which depends on r, so it becomes a vector field. So this is some vector field. So equation number 2 says that the magnetic field can be written as the curl of some vector field. Okay, so let's call this vector field as A. So this shows that B can be written as curl of A. So this is like a counterpart of what we had in the case of electrostatics. We saw that in electrostatics, the electric field, okay, at some point r could be written as the negative gradient of some scalar field, which is also a function of r, right? So here we call this as the scalar potential. So it means this is a electric field can be written as a space derivative of some scalar quantities. Similarly, the magnetic field can be written as, because curl is also a space derivative, so it can be written as a space derivative of some other quantity, some other field, but this time this is a vector field, not a scalar field like this. So this A, which is basically this integral inside the bracket, so this is called as the magnetic vector potential. Okay, so this is the expression for the magnetic vector potential. Given the current density J, we can find out the magnetic vector potential this way, and you can see that there is it mirrors the expression for the electric potential, because electrostatic potential, the expression is phi at r. You can see it just mirrors this. So instead of mu naught by 4 pi, phi at r, it was equal to 1 by 4 pi epsilon naught, then integration, it's a volume integral of what? Instead of J, we had rho, which was a function of r prime, and divided by modulus r minus r prime into d tau prime. So this was the most general solution for the Laplace equation, which gives us the electrostatic potential. And you can see here, this is a mirror of these two expressions. They are basically mirrors of each other. One case it's a vector potential, in the other case it's one case it's a scalar potential, in the other case it's a vector potential. So now we are having two potentials, one is phi, another one is A. So instead of calling it as electric potential, this as electric potential and this as magnetic potential, we just refer to phi as the scalar potential and A as the vector potential. So this finally gives us this important relation, that is divergence of B is equal to 0. Divergence of B is equal to 0. How does it follow from here? Because you can see B can be written as curl of A, okay, and this is a relationship which this is a relationship in which I had taken from the first chapter in Griffiths, that is for in general any vector field, okay, any arbitrary vector field V, the divergence of the curl of the vector field is always going to be 0. Okay, so if I consider that vector field to be A, that means the divergence of the curl of A, this must be equal to 0. Now what is curl of A? Curl of A is nothing but the magnetic field. So this means that the divergence of B, it must be 0. So from here onwards, I mean you can interpret this as the absence of magnetic monopoles, or the fact that we have magnetic field lines, they don't have any starting or end points. Okay, so this is basically the you could call this as the Gauss law of magnetic fields. So divergence of B is 0. So we have found out that divergence of the magnetic field is 0. Now next, what about the curl? Okay, let's try let's make an attempt to find out what is the curl of the magnetic field. And this is where in our attempt to find out the curl of the magnetic field, the expression that we arrive at, that expression is going to be the so-called Ampere's law. So this is what we have obtained. This was our equation number 2. That is, the magnetic field we are able to write as the curl of some vector field. That vector field is a vector potential. So this is the expression that we have. This is what we have obtained. Now we would like to find out what is the curl of the magnetic field. Okay, so what is the curl of B? To find out the curl of B, okay, mu naught by 4 pi, it's a constant, so it comes outside. So basically, when you're taking curl on the left hand side, you have to take the curl on the right hand side also. So what we have is curl of B is equal to curl of there's already a curl here, so curl of this integral. Okay, so if you try to find out the curl of this one, this is what we end up with. So we'll just call this as equation number 3. So curl of some vector field, this is what we need to evaluate. Now we already have an identity, okay, that is the second derivative. Okay, so the second derivative of when you consider the curl as the derivative under consideration, so the second derivative, that is curl of any vector field, is equal to gradient of divergence of that same vector field minus the Laplacian of the vector field. This is a result which again I have picked up from Griffiths section 1.2.7. okay, the very same result. So we can actually use this over here, and we can split this into two parts. So we have here curl of J. Okay, so this is going to give us gradient of the divergence of, okay, this is the vector field. I mean, this is our V. Okay, V is this entire integral, that's the V. So we have gradient of the divergence of this integral minus the Laplacian of V, Laplacian of this integral. So this is what we have. So it's a simple application of this identity on equation number 3. Okay, so now let's see if we can simplify this further. So we have here mu naught by 4 pi. We have there's already a gradient outside. So now this divergence, I can always take it inside the integral. It doesn't matter because this divergence is with respect to this variable, which is this divergence is with respect to this variable r, and the integration is with respect to the variable r prime. So this integration and this divergence, they are independent of each other. So I might as well take the divergence inside the integral. So it becomes divergence of 1 by r minus r prime into j, okay, minus the Laplacian of this. Okay, so now the first integral, let's look at the first term over here. The first term is basically, if you look at the integrand in the first of the first term, we have the divergence of, we have a product here, right, and this is 1 by r minus r prime. This is a scalar field, and then j is a vector field. So the divergence of the product of a scalar and vector field, this is equal to the scalar field times the divergence of the vector field plus the vector field dot with the gradient of the scalar field. This again is a result which I have just picked up from Griffiths. Okay, so you can refer to this particular equation in Griffiths. So this is exactly the same thing that we are doing over here. So we can actually split this into these two parts. So this is what it does. Okay, it leads us to a very ugly looking expression, but we'll simplify this even further. So we have the first term. So we have divergence of, okay, so what is f? F is 1 by modulus r minus r prime, so that is our f, and v is j. So what we have is f into divergence of v. So f, which is 1 by r modulus r minus r prime, times divergence of j. So divergence of j divided by modulus r minus r prime, plus, so we have j dot the gradient of 1 minus r minus modulus r minus r prime. So this is what we get. Okay, so now this quantity is going to turn out to be 0. This quantity is going to turn out to be 0. Why will this quantity turn out to be 0? The reason for this being 0 is, you see, j is a function of r prime, and this divergence, this is del, this is a divergence. You are doing this divergence with respect to r, and j is a function of r prime. R and r prime, they are independent of each other. So the divergence of j with respect to that is the divergence of j, which is a function of r prime, that is going to turn out to be 0. So the first term turns out to be 0. Okay, so this leaves us with only this term. So we have here already there is a gradient. So we have mu naught by 4 pi gradient of integration of j dot gradient of 1 by modulus r minus r prime minus mu naught by 4 pi, then integration of, then there is a j here, this j will come outside because j it depends, again the same reason, j depends only on r prime and this Laplacian is with respect to r, so j will come outside, so we are just applying the Laplacian directly on modulus 1 by modulus r minus r prime. So let's call this equation number 4. So now we are going to use two of these results. The first result is very straightforward. So you are taking the gradient of 1 by modulus r minus r prime, that will be equal to minus of the gradient nabla prime of 1 by r minus r prime. So what is the difference between this gradient and this gradient? In this gradient we are differentiating with respect to r, in this gradient we are differentiating with respect to r prime, and because r prime has got a minus sign, so when I make this transition from this differentiation to this differentiation, that extra minus sign is going to come. Okay, so this is what we are going to place over here. So this nabla, I'll replace it with nabla prime, so that will give us an additional minus sign. And the second one is it will help us to write this Laplacian in terms of the Dirac delta function, the 3-dimensional Dirac delta function. So the Laplacian of 1 by r minus modulus r minus r prime is equal to minus 4 pi delta cube of r minus r prime. So this again you can refer to Griffiths for this particular expression. Okay, so Griffiths he uses this notation, this stylized r to represent a separation vector. So there is r minus r prime, he writes it in this way. So that's what I have done over here. So this is the same expression. Okay, so this is what we have, and then now we substitute these back in equation number 4. So when we do that, this is what we get. So curl of b same as before. So here we have replaced this gradient with gradient prime, so as a result we will get an extra minus sign, so minus mu naught by 4 pi gradient of the volume integral of j dot nabla prime of 1 by modulus r minus r prime plus, okay, then this minus is going to become plus because there is a minus sign here, so mu naught by 4 pi, so we have j which comes from here, and then this is going to give us 4 pi delta cube. So 4 pi delta cube is this is what we place over here. All right, so now this is going to give us this is what it is. So now just a rearrangement, this 4 pi and 4 pi will get cancelled. Okay, so this 4 pi and this 4 pi will get cancelled, and as a result this is what we will get. And finally this, when you evaluate this integral, that is just going to give us j. And how do we get that? That is a property, that's a feature of the Dirac delta function. Okay, the feature of the Dirac delta function is if I have any function of r, okay, when I take the product of this any function of r, multiply it with the Dirac delta function at r minus a, okay, and take the volume integral. So basically we are sampling this function at this point a. Okay, so this is what the Dirac delta function does, it samples a given function. So when I multiply j with this the Dirac delta function, j is a function of r prime, and the Dirac delta function, it has got both r minus r prime, so we are basically sampling j at the position r. Okay, so this gives us mu naught into j of r, and this one more other term which contains an integral. So the integral on the first term on this side, it can be simplified further by using integration by parts. That is, we are going to use this result, which again I'm taking this result from Griffiths, from this particular section and page which is given here. So we use the integration by parts, this same rule, and over here we simplify, we just retain this term on the left hand side. So we have minus vector field dot gradient of scalar field is equal to volume integral. So minus volume integral of the vector field dotted with the gradient of the scalar field is equal to the vector field, so the volume integral of the scalar field times the divergence of the vector field minus the scalar field and the product of the scalar and the vector field, which is taken as a surface integral. Okay, and what is this s? S is the surface which is bounding this volume tau. Okay, so we can now just apply this over here, and you can see the correlation. The correlation here is this. the correlation here in this case is, if you compare it, this one with this, if you compare it here, your V, okay, is your J, vector J, and F is 1 by modulus R minus R prime. So when you make this substitution, this is what we get. So the above integral, this is what it becomes. It becomes minus J, okay, J of R prime dot gradient of 1 by R minus R prime d tau. This is equal to, we are having divergence of V, V is J, so divergence of J times F, which is 1 by modulus R minus R prime, minus the surface integral of F into V, which is 1 by R minus R prime into J, so J by R minus R prime, so J by R minus R prime dot N prime cap into dA prime. So this the volume integral was carried over the volume tau prime, and S over prime was the bounding surface of tau prime. So this in this integral on this side, this is this integral, it gives you these two terms. So in the above integral, in the above expression, that is in this expression, the surface integral, which is the second term, this is going to vanish. Okay, why is this going to vanish? It is going to vanish because of two reasons. First reason is, like I had mentioned, when we integrated over tau prime, we had assumed that the current is the current density J is contained totally within tau prime. Okay, so the flux of J through the surface is 0. So essentially this is what we are talking about. So we have some volume, okay, so we have some volume tau prime, okay, which is bounded by some surface S prime. So S prime is the surface. So what you're saying is, this current density, it is contained totally inside this one, okay, so it might circulate here and there, but the current density J, it is contained totally inside, which means none of these, none of the currents, they actually come out of the surface. So if they don't come out of the surface, that means the flux of J, okay, the flux of J is 0, because what is flux? Flux is how much of a vector field is crossing a surface. Okay, but we are assuming that the J is contained totally inside this volume. So because J is totally contained inside this volume, that means J does not cross the surface anywhere. So that means the flux of J is 0. Okay, so that's the first reason. Okay, so therefore this flux is going to be 0. But then there is a possibility that, you know, you could have some surface current, because we know that there could be surface currents also. Currents could also flow over the surface of a volume. But then even if we have some kind of a surface current, okay, what is going to happen is, let's say I have some surface current, let's say some surface current over here, let's say we have some surface area, so this is some surface area, and then let's say there is some surface current, let's say K, okay. But even if we have some surface current, but then the normal vector, it is going to be perpendicular to the surface current. So then again K, but you could just write this as J. Then again because the surface current is perpendicular to the normal to that surface, so therefore their dot product, again it's going to be 0. Okay, so J dotted with N cap prime is going to be 0, even if, let's say, there is some kind of a surface current which is circulating over the surface of this volume. So in either case, the current does not come out of the surface, even if the current is on the surface, but its dot product with the normal to the surface is always going to be 0. So as a result, this quantity, which is the second term, this is going to turn out to be equal to 0. This quantity is going to turn out to be equal to 0. Okay, so this leaves behind just one term, and then we just plug this back. So we have just one term left, that is this term, and this term we plug it back into this expression. So already we have minus mu naught by 4 pi. Gradient of this quantity is what we are trying to find out, and this quantity which we are trying to find out here is basically this. So gradient of this integral, so that's what is left. So gradient of this integral, and there is already a mu naught by 4 pi. So the curl of the magnetic field, this is what it turns out to be. Okay, so the evaluation of this integral on the right hand side, it of course depends on the form of the current density. So without really knowing what kind of current density we have, we cannot actually proceed and find out this one. But then we can always simplify this in the case of magnetostatics. Okay, so in the case of magnetostatics, that is, in case it's a steady state phenomena, that means the current is steady. So current is steady means if I the dou rho by dou t does not change. So let's try to understand what this means. So we have this volume, steady state. At steady state, what happens? Steady state means the current remains steady. So let's say I take some area of cross section. Okay, I have some area of cross section. So I in the steady state, what happens is this J remains constant with respect to time. J does not change. So if J does not change, then if I take a volume, okay, if I take a certain volume, the amount of charges which are crossing this volume, because J is steady means the charges are flowing at a steady rate. So the amount of charges which are flowing per unit time through this volume, that also is going to remain the same. So it means at any point of time, the density of charges inside this remains the same. So if the density of charges remains the same, then the derivative of the charge density, okay, with respect to time, this is going to be 0. This is not changing with time. So in the steady state phenomena, this is what is going to happen. Dou rho by dou t is going to be 0. If dou rho by dou t is 0, that means the divergence of J is 0. And how did we get this? We got this using the equation of continuity. Okay, so once we get this, then this integrand is going to be 0. So then this overall, so in the case of magnetostatics, this entire second term is going to go to 0. Okay, so for steady currents, we have curl of B is simply going to be equal to mu naught into J. So this gives us the expression for the curl of magnetic field, and this is the so-called differential form of the Ampere's law. Now from there, just one step, you can find out the integral form of the Ampere's law just by using the Stokes theorem. So you just integrate both sides with respect to over some arbitrary surface S. Okay, and then by using the Stokes theorem, on the left hand side, this curl of the surface integral of curl of B is going to become the line integral of B over some closed surface, and this is going to of course give me, because this is the flux of J, so flux of J means it's going to give us the current which is enclosed. So we get, so this is basically the integral form of the Ampere's law. So here we have it. So we have the divergence of B. So we have these two relations that we have here. So we have the divergence of B, which we showed just some time back. Divergence of B, using the concept of the magnetic vector potential, we found that the divergence of B is 0, and then the Ampere's law, it tells us that the curl of B is equal to mu naught J. Okay, and later on when we study the electromagnetic waves, we will realize that this is actually not correct. There is one more term which is going to come, that is that takes into account the transfer of energy. Okay, the transfer of energy over, let's say, a situation. Let's say I have a capacitor. So that leads us to a current which was defined by Maxwell as the displacement current. Okay, so that was the correction which was made by Maxwell, and it becomes, in that case, it is no longer called the Ampere's law, it is called as the Ampere-Maxwell's law. So that's about the Ampere's law. So with this, I come to the end of this lecture. Thank you.